Welcome back to our office here in Western Oregon, where it is still spring and I'm still suffering from hay fever. So please forgive me if I have to take a break during the lecture. Today we'll start our discussion on partial differential equations, or PDEs as they're commonly known as. And this introductory session will just be some generalities about how you solve partial differential equations, the types of PDEs, and how we'll go about figuring out an algorithm for them. So let's get on with it. Should not be very hard. What's the difference, first of all, between an ordinary and a partial differential equation? They're both differential equations, but the ordinary differential equation usually deals with one independent variable, and partial differential equations deal with more than one. It's as simple as that. So if we have, for example, a field in a general physics type, mathematical physics sense, a field which depends on space, possibly time, we describe that usually with a differential equation. If it has just time dependence in it, then we could do ordinary. Just one variable. If it has multiple variables, we must use a partial equation. Okay? Physical quantities such as pressure, temperature, as you know, vary continuously in space and time, and therefore are very easy to describe and appropriate and natural with some kind of a differential equation. And that's because changes in the field at any one point in space-time tend to influence the neighbors. Okay? So you can talk about a differential change. So most of the dynamical equations in physics are in fact differential equations. And to go further, since physics tends to deal with three-dimensional space and times, most of the dynamical equations in physics are partial differential equations. Okay? And in the real world, much of the engineering work involves solving partial differential equations. So we've done ordinary differential equations in the past. We have our Runge-Kutta technique for that. Now we need other techniques, similar but different, always different than the simple Runge-Kutta, in order to apply it to functions or fields that have multiple variables in them, multiple dependent variables. So let's look at the next slide. The next slide, slide 7, talks about the different forms of differential equations. So we see here the partial differential equations are usually described in 3 sets. And I didn't make up these terms. They don't mean a lot to me just by their name, but you learn what they are. So the most general second order differential equation. Why second order? Well, that's what nature seems to have. Most everything can be described as just, second derivative plus first derivative. Sometimes it's a third derivative, but basically it's all differential equations of the form in the heavy dark blue title there. And what you see there is that we have derivatives of a variable, the field, second derivative, one variable, second derivative, mixed, second derivative, other variable, first derivative, and another first derivative. A, B, C, D, and E, and constant F are just arbitrary functions. They can be functions of space and time as well, but the actual field that we try to solve for, U, is written as in this differential form. And depending on the values of capital A through capital F, we have different kinds of partial differential equations. Elliptic partial differential equation has D, the discriminant, determinant, a product of AC minus B squared is greater than 0. So you can think of it, an elliptic differential equation is like Poisson's equation. If we look at Poisson's equation here, del squared, which is the derivative with respect to x, y, and z, second derivative, is equal to minus 4 pi rho. In elliptic, all the derivatives in second order, and they all have the same sign when placed on the same side of the equation. So all of the second derivatives enter here with a positive sign. That's an elliptic differential equation. In a parabolic differential equation, such as the heat equation, which has del squared, so again, that has all the second derivatives, is equal to some constant times a space derivative. There's one derivative of first order on one side of the equation with a positive sign, the other on the second. So that's a parabolic, which has both the first and second mixed in this form. It could be on either side, but this mixture makes it parabolic. And finally, there's hyperbolic, and that, such as the wave equation. We have the space derivatives on one side, positive, and then we have the time derivative, all second order, on the other side, also positive. So if you bring the time derivative over, we'd have one set of derivatives, usually time, with opposite signs, and that's what makes this a hyperbolic differential equation. So I wouldn't memorize elliptic, parabolic, hyperbolic. I mean, you see the terms always. You could look up what they mean. But if you remember, elliptic is like Poisson's equation, parabolic is like the heat equation, and the wave equation is a typical hyperbolic, then you know what we're talking about. Those are the three basic types of differential equations. So what about them? So let's look at this next slide, which, G, has a lot on it. Well, we want to solve a differential equation. And in ordinary differential equations, we always have to have some initial conditions to solve it. That's true for partial differential equations as well, except you really need more initial conditions because there's more variables. Whatever the number is, 2 or 3 times as many variables, you need that much more information. So we always have initial conditions. But then, in order to find out if there is a solution, in order to determine the physical situation of what you're trying to solve, in order to describe the problem you're solving, you also must have boundary conditions. Because usually there's just not enough initial conditions to specify the problem completely. You have to say what's happening on the boundary. So both of these are required in order to have unique solutions. But that in itself is not necessarily enough, or that could be too much. Okay? So we usually break up the kinds of boundary conditions that can occur in nature, or mathematics if you want, by saying they're either Dirichlet, Neumann, or Cauchy. And Dirichlet, you have a surrounding surface which contains the interior where we solve the problem. So there's a surrounding surface, and the solution, U, as we've had on the previous slide, the solution U is known on that closed surrounding surface. And the fact that it's closed is very important because that means we have a well-determined problem. If we know the value of the normal derivative of the solution, okay, so that's a normal derivative on the surrounding surface, which completely encloses everything, then we have what's known as a Neumann boundary condition. And Cauchy has both the solution U and derivative is known on a closed boundary. So that's a lot of information, and sometimes the statement of the problem tells you all that. So now we look and we see, okay, what are the required boundary conditions for the 3 different types of partial differential equations? Dirichlet is usually what we like. That's saying we know the function on a surrounding volume. That's good. And as you see here, though, for an elliptic problem, such as Poisson's equations, that's underspecified. We need more than that. For a hyperbolic, such as a wave equation, it's also underspecified. But for a parabolic equation, that's unique and gives us a stable solution. So if we have an elliptic problem, we'd have to have a Dirichlet on a closed surface, okay? And that means, completely enclosed, it's known, then we have a unique and stable solution. Okay? And that's what we'll look at first of all. But if the surface is open here, so there's some region where the solution is not specified, that's not enough information. You can't solve the problem. Well, that's not true. You can solve the problem. That's the whole problem. That you can solve it, and there's infinite number of solutions. It's not determined well enough. It's not unique. Okay? So that's not to say you can't find the solution, but the solution depends on assumptions we've made. Clearly, the assumptions you make about what's happening in the open region. Okay? If you have Dirichlet, which is, again, complete value on an enclosed surface, that's overdetermining a problem such as a hyperbolic wave equation, and it's overdetermined a problem for a parabolic. So you'd say, overdetermined, that's okay. I like to be sure of things. I've told you more than you need to know. What's wrong with that? Well, what's wrong with an overdetermined problem is that it's too much information, it's too demanding. You may not be able to find the solution that satisfies this. So a solution may exist, but it may not exist. And most likely it doesn't. Okay? It's too high a demand. Okay? And likewise, we have, I don't have to go through all of these, the different possible boundary conditions. You can have unique solutions or you can have overdetermined. Usually, if you're a physicist, you'd say, if it's a well-defined physics problem, then it should have a solution. And that's true. But sometimes you're making assumptions about what the boundary conditions are, as I'll try to emphasize, and that's telling you what the solution is. So it's good to be aware of that. So that's all for these introductory remarks. Let's get on. And I suggest you first look at the lecture on Poisson's equation, Laplace's equation, static electric fields, because that's about the simplest, and that shows us one of the basic techniques. So let's get on and start looking at that now. Bye-bye.